In the previous lectures, we found out the displacements and slopes in certain simple beams, and further we found out the fixed moments due to UDL alone in a fixed beam and an eccentric or concentric point load in a fixed beam. Now further, we may encounter situations in the flexibility method or stiffness method, like if we have a beam like this, one end is say roller supported and the other end is say fixed, and if you apply a moment here MA, what is the slope at this end? Say theta A is the slope at end A. Theta A due to applied moment MA may be a question. Sometimes we have to apply this result in many situations in the flexibility as well as stiffness method. Now I have drawn the bending moment diagram due to MA alone in this figure. This is a sagging bending moment diagram, so positive sign, and because of this MA, a moment MB is induced at the other end, so that there is no slope over there, and MB introduces a bending moment diagram like this, a hogging BMD like that. Now if we exploit the compatibility conditions in the method of consistent deformation, that is, the slope at this end is equal to theta A and the deflection at this end is equal to 0, we can write the slope theta A at this end given by moment area theorem due to MA into L divided by 3EI, and slope at this end due to an induced moment MB at the other end minus MB into L divided by 6EI. Again the minus sign is because the slope induced by a clockwise moment here would be anti-clockwise. Rotation here is going to be anti-clockwise because of that. That's why the minus sign, and the rotation at this end due to a clockwise moment there would be positive, clockwise. So this is clockwise rotation, that is anti-clockwise rotation. So if you reduce the equation, you may get MA minus, let us say 2MA, if you multiply throughout by 6CI by L, this is 2MA minus MB is equal to 6EI theta A divided by L. So equation number 1. Now deflection at this end, or the deviation of the tangents down to point A and point B at this end would be given by deviation is equal to 0, actually, that is equal to one by EI into area of BMD, that is MA into L divided by 2 EI into distance of the BMD with respect to this end. This will be L by 3. From this bending moment diagram, we have minus MB L divided by 2EI into distance of centroid from this end will be 2/3 of L. If you simplify that, if you multiply throughout by say 6CI by L, you are going to get MA minus 2MB is equal to 0. Equation number 2. If we simplify these two equations, like equation number 1 minus 2 times equation number 2. This time will cancel. Minus mb minus 2 times this 2 mb would be 3 mb is equal to this minus 2 times this 6 ci theta divided by L. That's fine. So mb is equal to 2 ei theta a divided by L, and ma in terms of theta a is equal to, using this equation, ma is equal to 2 times mb, that is 4 ei theta a divided by L. We can also write the slope theta a in terms of the moment. Say theta a in terms of ma would be equal to L by 4 ei into ma, and theta a in terms of mb would be L by 2 ei into m. Now further, let us have a situation where one end is fixed in a beam and the second end is also fixed, but there is support settlement. Suppose this support moves down by some distance delta. So this is original B, now this is B prime. This displacement is delta. So this is the deflected shape of the beam. Because of this, there would be a moment induced over here, called that as MA, and a moment induced over here, that is called that as MB. So due to lowering of the right end with respect to the left end, the moment induced are MA and MB clockwise. The bending on diagram can be split into two parts. This for MA and this for MB as before. The compatibility conditions are the slope at end B is equal to 0 and deflection at end B is equal to delta downwards. Now, if you write down the equation for slope, say theta B, which is actually equal to 0, would be the angle between the tangents down to point A and point B. That is, as per the moment area method, it is 1 by EI into the total area of the BMD between the 2 points. If I follow that, let me put 1 by EI outside, within bracket, area of this BMD MA into L divided by 2. Area of this BMD, of course, with a minus sign, MB into L divided by 2. That is equal to 0. If you follow this equation, we can observe that MA is equal to MB. That is equation number 1. Further, the deflection at this end is equal to delta downwards. So the deviation of end B with respect to end A given by the moment area theorem will be equal to the deflection. That is equal to 1 by EI into moment of this BMD with respect to end B and moment of this BMD with respect to end B. So we require the distances corresponding to the other end. We require this distance, which will be L by 3 in this case, and this distance of centroid of the BMD about end B, which will be 2L by 3. So moment of MA divided by MA into L divided by 2 with respect to this end would be into 2L by 3. Moment of this BMD about this end would be minus MB L divided by 2 into L by 3. And that is equal to delta downwards. We have to put a minus sign for that for sure. Because you see the deflection produced by MB is downwards, that is why we put a minus sign. Here also we have a minus sign and here also we have a minus sign compatible to the deflection produced by this moment in this equation. Now if we simplify that equation, we are going to get two MA minus MB is equal to minus 6 EI delta divided by L square. Equation number 2. If you solve equation number 1 and equation number 2, we are going to get MA MB is equal to MA, so you can put 2MA minus MA. So 2MA minus MA is MA is equal to minus 6EI delta divided by L square, and MB is equal to same minus 6EI delta divided by L square. So in essence, if there is a lowering of the right end of the fixed beam with respect to the left end, the moments induced at the left and right ends would be anti-clockwise 6CI delta divided by L square, where delta is the lowering of the right end with respect to the left end. E, I, L are the properties of the beam.